The topic of Lesson 9.1 is reflections. You will draw reflected images and recognize and draw lines of symmetry and points of symmetry. Where are reflections found in nature? On a clear, bright day, glacial-fed lakes can provide vivid reflections of the surrounding vistas. Note that each point above the water line has a corresponding point in the image in the lake. The distance that a point lies above the water line appears the same as the distance its image lies below the water. In geometry, a reflection is a transformation representing a flip of a figure. Figures may be reflected in a point, a line, or a plane. The figure shows a reflection of ABCDE in line M. Note that the segment connecting a point and its image is perpendicular to line M and is bisected by line M. Line M is called the line of reflection. For ABCD and its image, A prime, B prime, C prime, D prime, E prime. Because E lies on the line of reflection, its preimage and image are the same point. And they add little marks for each time you do another transformation to the same image. It is possible to reflect a preimage in a point. In the figure below, a polygon UVWXYZ is reflected in point P. Note that P is the midpoint of each segment connecting a point with its image. When reflecting a figure in a line or a point, the image is congruent to the preimage. Thus, reflection is a congruence transformation or symmetry. That is, reflections preserve distance, angle measure, betweenness of points, and collinearity. In the figure above, polygon UVWXYZ is congruent to U prime V prime W prime X prime Y prime Z prime. For example 1, they ask us to draw the reflective image of quadrilateral WXYZ in line P. The first step is to draw segments perpendicular to line P from each point W, X, Y, and Z. Next, we need to locate W prime, X prime, Y prime, and Z prime so that P is the perpendicular bisector of each segment. Now, when I do that, I usually take a piece of scratch paper and I will make a tick mark to see how long we are from Y to P, line P, and then I will use that to mark that same distance on the other end. You could measure these with a ruler, but a piece of scratch paper works real well because then you don't have to worry about the accuracy of your measurements. And then finally, the fun step is connecting our new translated vertices, and voila, we have reflected over the line. Okay, these should look familiar. We did these in the Algebra 1A course. And actually, we did rotations in the same lesson. That was a brilliant move that book made. Okay, so in geometry, we're only doing reflections. That's a good idea. So to reflect over the x-axis, we just replace our b with negative b, or multiply the y-coordinate by -1, which makes sense. Instead of going 3 units up, I want to go 3 units down. Instead of going 1 unit up, I want to go 1 unit down. That reflects me over the x-axis. So the reflector of the y-axis, I'm going to do the opposite of x. So instead of 3 units to the right, I want to go 3 to the left. Instead of 1 to the right, 1 to the left. So we're just multiplying the x-coordinate by -1. To reflect over the origin, we're going to multiply both of them by -1. So 3, 2 becomes -3, 2, and 3, -1 becomes -3, positive 1. And to reflect over the line y equals x, which, remember, is a nice 45-degree angle there, cuts right through the first and third quadrants, up 1 over 1 from 0, 0. So this is kind of an interesting one because they switch. Instead of 1, 3, it becomes 3, 1. Instead of -3, 2, it becomes 2, -3. So you're just interchanging your x and y coordinates. Now this table is worth taking some time and copying down. Maybe not all of the examples per se, but you definitely want the rules. They will help you out greatly. For example 2, they gave us quadrilateral ABCD with the given vertices. graph ABCD and its image under reflection in the x-axis. Compare the coordinates of each vertex with the coordinates of its image. So I put in here our rule for reflecting over the x-axis, which we want to do the opposite of the y-coordinate. So 1, 1 becomes 1, negative 1. 3, 2 becomes 3, negative 2. 4, negative 1 becomes 4, 1. And 2, negative 3 becomes 2, 3. We've already graphed our pre-image, and now we can plot the points for the image. And when we connect the points, we can see what it looks like when we overlap, because our original image, pre-image, went over the x-axis, so our image will overlap it. It's kind of nice how they used colors there, because it's kind of easier to see. If you use a pencil and it's all black, it kind of looks like a big old blob. So colored pencils might be a good idea on these. For example 3, they want us to reflect over the y-axis. So to reflect over the y-axis, we're going to do the opposite of x. So 1 becomes negative 1, 3 becomes negative 3, 4 becomes negative 4, and 2 becomes negative 2. And they ask us to graph the image and pre-image. So the pre-image is already there in yellow, and we're starting to plot points for the image. So that's a nice one to see reflected over the y-axis. It's not so bad because the original pre-image did not overlap over the y-axis, so the two do not overlap. For example 4, they'd like us to reflect it over the origin, so our rule is pretty simple. We're just going to do the opposite of both coordinates a and b. So our original graph is there, and then we're going to do the opposite of both x and y. And so this is a more interesting reflection when we go around the origin. Instead of going, originally we were going over 1 up 2, now we're going backwards 1 down 2. So it's the complete opposite for every point. For example 5, they want us to reflect over the line y equals x. So we have a simple rule there too. We're just going to reverse our x and our y's. So 1, 2 becomes 2, 1. And if I kind of roughly draw in the line y equals x, you can see how it is reflected. So for A, I was going up over 1 up 2, now I'm going over 2 up 1. During a game of table tennis, Dippa decides that she wants to hit the ball so that it strikes her side of the table and then just clears the net. Describe how she should hit the ball using reflections. She should mentally reflect the desired position of the ball in the line of the table and aim toward the reflected image under the table. Some figures can be folded so that two halves match exactly. The fold is a line of reflection called a line of symmetry. For some figures, a point can be found that is a common point of reflection for all points in the figure. This common point of reflection is called a point of symmetry. The four-letter F does not have any lines of symmetry. The isosceles triangle has 1, this has 2, this has, more than 2. These first two figures also have no points of symmetry. This guy does. Each point in the figure must have an image on the figure for a point of symmetry to exist. So there's an image of here, and so on. And a point of symmetry is the midpoint of all the segments between the pre-image and image. So a circle, obviously, yes, would have a point of symmetry. Determine how many lines of symmetry a regular pentagon has, and determine whether a regular pentagon has a point of symmetry. Well, a pentagon has 1, 2, 3, 4, 5 lines of symmetry. But unfortunately, I am not able to find a nice happy, there's not a reflected point across there. So the short answer are 5 lines of symmetry, but no point, because I can't reflect.